Okay, so tonight, actually interesting. Scott was the one that was bugging me about maybe doing a little program on the Nano VNA, and this is a really neat little product. And this is just kind of an overview of VNA and what it is, what it means, what it does for you. But it's a really neat little device that's a antenna analyzer, basically. But it does a whole lot more. So this guy is going to be a, let's see here. So there we go. So this is, I'm just doing a basic, covering the basics of the DNA of the VNA. So nothing in much, a whole lot of details. So this is really an antenna analyzer. So, some hams out there only want to know if they have a good SWR. They really don't care about why or anything or any reason why. They just want to see if they have a good SWR. So simple analyzer. So all your antenna analyzers, no matter what they are, they'll always tell you what the SWR. Now they don't tell you necessarily how you get it or how to fix a problem if you have a bad SWR, but it will at least tell you SWR. And people that don't have a real good SWR, they're always happy to put an antenna tuner in there, and that just takes care of the problem that you might have a dodgy SWR for the antenna tuner. But it doesn't mean that, or just means that you're not out there looking at the antenna trying to figure out what's going on. So other hams want to know how to maximize their antenna performance because usually an antenna that has a dodgy SWR means that you got some losses up there, and all your transmit signal, all your receive signal isn't really going to be optimized. So if you really want to know why your antenna isn't performing correctly, a good high quality antenna analyzer with some new good features in it will certainly help tell you where the problem is. Once you know the problem, you can kind of figure out how to fix things. Before using a new or used antenna, so this is me, or a new antenna or a piece of coax or something like that, I have a tendency to go through there and run it across my antenna analyzer and take a look at it to see if there's a problem. I really don't want to hook up a bad antenna or even a new piece of coax that I don't have confidence in that it's 100% correct. So that's just me as far as making sure that I don't blow things up. Same way, like if I get a brand new rig, before I put it up on any kind of antenna, I want to know how well that thing works. So I always connect it up to a dummy load and some monitoring equipment, and then I apply the old transmit power and see how well that thing works. But I like being a little bit cautious about that. So antenna analyzer, that's probably the number two tool for any ham out there. Number one being a digital voltmeter out there, and that's just a basic um, test piece of equipment that I'm sure anybody that works in electronics or around electronics has. But for us hams, we need to know what's going on in the RF domain, and so we really need to have a good antenna analyzer to help us to understand what's going on. So all your antenna analyzers will certainly display your SWR. Most will display impedance. Impedance tells you the resistance. We know that all the ham radio equipment is built to expect a 50 ohm impedance there. So a good antenna analyzer will tell you how far off you are from that ideal impedance. Some antenna analyzers will have advanced functions to diagnose antenna systems and bandpass filter problems. So you step up to something that's a little bit better, it's going to basically tell you a whole lot more out there. So I think everybody have seen this guy, MFJ 259 out there. This is the old original antenna analyzer that changed the world for ham radio operators. Before this came along, antenna analyzers were pretty much out of the reach for most general hams. They were just way, way too expensive. They cost, $20 to $40,000 or more to get a decent antenna analyzer to help figure out what's going on. The other thing, back in the old days, a lot of times, a lot of hams really didn't understand or know about matching your transmitter to your antenna. Most of your rigs there were made out of tubes, and they are always very, very forgiving about a bad antenna match up to a point. But once we got finished with World War II, then 50 ohm coax came onto the market, and everybody migrated to that standard. And a little while after, we had this MFJ antenna analyzer that came along. And that was the one device that probably did more than any other piece of test equipment for the ham community to really to figure out what's going on. So it enabled the hams to experiment with antenna design. And that's something we didn't have before. And so that came up with a lot of really cool designed antennas and proof of concepts, and also came up with some really nice antennas that work better with more modern rigs. So this device, I would say, was the most significant contribution that has ever been made to the ham radio community. That MFJ antenna. So since then, there has been all kinds of new analyzers that have come onto the market. We've especially seen that in the last 5 or 6 years. Lots of new ones. And we're very innovative. Some better in prices, some worse in prices. The old MFJ antenna analyzer was not very accurate. And so with each new generation, they become a more and more accurate and provide more and more features. So back to the subject on SWR. And SWR is a direct relationship to what you have for a mismatch impedance. If the impedance of a feed line and antenna match, all of the power, in other words, if it matches the 50 ohms that's expected, all of the power will be transferred to from that antenna. Remember, this is also, it's an issue with transmitting. It's also an issue, reciprocal issue for receiving. If they don't match, some of the power is reflected back to the transmitter, and that's called a standing wave radial, SWR. SWR is an indicator of how well the feed line and the antenna is matched to 50 ohms impedance. So the SWR is a ratio between feed impedance, that's where the antenna analyzer picks into or gets into, and the characteristic impedance of 50 ohms through your feed line and to your antenna. But the key part here is that it's a ratio. So let's look at, this is the only technical slide that's in this whole thing. Impedance, and it's normally referred to as Z when we look at it in formulas. Impedance is formula is Z equals R plus JX. So R is the real impedance, the real AC impedance, or the real RF impedance, I should say, not AC, of whatever you're driving, whatever you have for a load out there. And X is a thing called reactance, and that's imaginary. So AC, or excuse me, your reactance is non-productive resistance, so it doesn't really radiate for you. It doesn't do anything for you. It may add, make, subtract, or do something for your overall impedance. So a good antenna analyzer is going to be able to look at that impedance and determine if it's an inductive or if it's a capacitive. And then we can get into antenna theory and figure out how to get in there and fix the problem and make it correct for you. So here's a really neat chart. It kind of shows what you have for losses. So this chart is based on a 100-watt transmitter. So if you have an SWR 1-to-1, that means all your power is going to get to or have the ability to be radiated on an antenna. Now, just because your antenna has a nice 1-to-1 match doesn't mean that that efficiency on that antenna is going to be able to radiate 100% of that power. So you can see a 1.5 there, you have about a 4% loss. 2-to-1, you get to 11%. Most of your solid state modern day transmitters will work very, very nicely all the way up to about a 2-to-1 SWR, and it won't have any problems. As you get into the higher SWRs, it has more and more problems. And as you see in the 2.4 and 3.0 to 1 SWR, that's kind of the yellow line there, where depending on the transmitter, it may end up backing off on the amount of power that it will try and transmit, or it may end up disconnecting you. But this is kind of the danger zone there, where if you continue to transmit at full power, you're going to generate a lot of heat in your finals, and that may toast it, or you may have something in there to prevent it from getting toasted and reduce the power or plain shut down. And normally, when you get on a solid state transmitter, a 4-to-1 or better, you're in the danger zone, and it's not very healthy for them to work in that area. And you can see the losses there also mount up quite substantially. So a couple of points here. Most amateur transmitters are, this is kind of a little bit of a repeat of what I just said. So most amateur transmitters are designed to operate or be able to tolerate up to a 2-to-1 SWR or lower. When you get to a 2-to-1 or greater, then you fall into the kind of a beginning of a danger zone, and transmitters will either disconnect or reduce the amount of power or monitor the heat sink for over temperature and then react accordingly. When you get into something that's above that, up to that, 3-to-1 or better, up to the 4-to-1 or better, then, solid state transmitters these days pretty much shut down. So one of the things that you can do is you can put a tuner in there, but I think everybody will realize that a tuner, what it does is that it fools the transmitter and thinks that it's transmitting into a 50 ohm load. But in the reality, how it deals with the feed line and the antenna, it makes up the difference. So if you have a 4-to-1 or 5-to-1 SWR, it'll do the matching for you. Now, I'm not bashing tuners. Tuners have a definite place that you need to use tuners. So here's a for instance. Think about the 80-meter band. 80-meter band is goes from 3.5 megahertz all the way up to 4 megahertz. That's a huge, massive band. If you have a dipole will not tune from one end of that band to the other end of the band safely. You cannot operate. It literally takes 3 different antennas to get from one end of that 80-meter band to the other in a safe SWR. So when you end up placing, so that is a situation where typically you use a tuner where everything in the mid band, no problems, but in the upper end of the band or down in the lower end of the band where you have digital FT8, that's where you need the tuner to end up giving you a better match. And there's many other examples like that. So, introduction, Nano VNA. You have 2 main flavors of that. The one on the left is has a 2.8-inch screen. It's smaller. It has a little bit limitation in capabilities, but it has a very small screen. And if you have fat fingers, that is a touch screen on there. To operate the menu, it gets pretty hard to end up doing it by finger. So the new kits out there either come with comes with usually a stylus or a guitar pick for ended up um, selecting information out of the menu and configuring it. So it comes with a couple jumper cables. It also comes on the left side there, lower left. You have four slugs there. Actually, you have three slugs for calibration, a short, an open, and a 50 ohm load that is used for calibration. The second tube that's in, that's just a coupler between your two test cables there. It also comes with a USB cable. That USB cable is a Type C USB cable for charging your um, VNA. So the machine over on the right, which is the one that I kind of prefer, that has a larger screen, a little extra price, and we'll talk about pricing in a little bit. So that's a 4-inch screen, much easier to see, much easier to configure. Still using a stylus or a pick makes life a lot easier going through there and doing the configuration. You still have the same number of cables. You have still the same slugs there for doing all your calibration for the device, but it has a nice bright screen. It's easy to take outside, and you have enough brightness there to easily see the screen and easily calibrate it when you're having to work in the field. Now, that device is also battery operated, so it has a battery that will last you several hours out in the field. I'm not sure how long it would last. I mean, I've easily run 2 hours on mine and not had a problem, but it runs a long time out there on just the battery. So the Nano VNA, the 2.8-inch screen, gives you 10 kilohertz. This is the frequency span on what it will cover to 1.5 gigahertz. Huge span there. And it'll do it all for about 60 bucks. If you step up to the 4-inch screen, you have the same span, 10 kilohertz to 1.5 gig, and that'll set you back anywhere from about 80 to 100 bucks. So that's not a bad, 20 to 40 bucks more for that bigger screen, and I much prefer that bigger screen. There's also several options out there in that larger size for obviously for more money. You can get one that goes from 50 kilohertz to 3 gigahertz. That'll set you back 140 bucks. You can get another version of that that goes from 1 megahertz to 6 gigahertz. So that'll get you through uh, both the 2.5 Wi-Fi band and also the 5 gigahertz Wi-Fi band. But that'll set you back $320. The other thing is that, being that this is a very popular device out there, and understand not only ham radio, it's not just ham radio operators use this device. There's a lot of different disciplines that use this guy, but you have to watch out for um, clones. And when you get on actually you get on the formal guy is the tiny VNA. You get on that website there, then they will end up going through there and no, excuse me, it's not tiny. It is Nano VNA. If you get on that wiki or that website there, they have a link there that'll tell you valid providers for it. And if they are not in the list, you probably don't want to buy from them. You can probably find these things cheaper, but what it means is that they've gone through there and substituted cheaper parts or maybe changed the design to use cheaper components. In the process of that, a lot of times the software that goes onto these guys will not be compatible with those clones, those knockoffs. So just beware of that as you make that selection. Another piece of equipment that I usually get or I've got in the past, and that's this VNA demo board. Costs you about 10 bucks there on Amazon. But this gives you test fixtures because there's a lot of different configurations that you run into um, on this Nano VNA. And it's really nice that you can plug into a test fixture where it gives you a picture of what things are supposed to look like. And then if you don't get the right picture, then you can hunt around and figure out what setting you don't have set right. So I really, and also this, if you end up frying it or screwing up something, or you have a bad cable, this is always a cool device here to end up going back and testing things out and make sure that things are configured correctly and functioning correctly. Another thing you'll need is that if you noticed on that Nano VNA, all the cable connections, and also there are other versions of this where that use the PL259s or use BNC, but they're not mainstream and obviously they cost more, but you can get those things with other type of connectors on it. So you notice that on that Nano VNA, those are SMA connectors, and you'll need something to bridge the gap between that SMA and whatever type of connector, the N type of connectors, 259s, B and Cs, or whatever you have out there. You will need a handful of extra adapters there. So what the heck is a VNA? Why is VNA so darn important to you? So VNA stands for Vector Network Analyzer. So what the heck is a vector? If unfortunately I'm not able to take and be in a room and do my usual animation that explains what a vector is, but a vector is nothing more than a mathematical form that represents a distance and a direction. If you look due north and you think about Portland up there, well, Portland's not exactly due north. It's probably from where we're at, where is probably 15 degrees to the east. So if we think of Portland, the distance is 90 miles with a phase angle of 15 degrees. So when we get into a VNA on the way it determines this, it basically takes everything and builds it as a vector. From the vector and how we look at different components in that RF signal, we can then derive SWR, we can derive impedance, we can also look to see what's our imaginary or not real resistance. All of those mathematical things can be derived from knowing that vector, that distance out there. Really important to know. So anyway, the VNA can make all these measurements, and it's insane the accuracy that you get out of this. This guy is really quite accurate up to a point. So I think everybody, or I don't know that maybe everybody, but one of the things I'll point out is that for all the ham stuff that we do, the basically from 1 megahertz up to 50 megahertz, that thing is very, very accurate. When you start getting up into the gig speed of things, then it becomes less accurate. They don't have quality enough components in there to deal with all the little things that you end up working up at that gigahertz and above range. It is fairly accurate, but not like what you have in the lower HF and VHF, UHF range. So how do we use this information? Well, that vector can give us the SWR. It can tell us about coax losses and links. It can tell us about impedance, it can tell about real resistance, inductive or capacitance, the reactive component stuff. It can also tell us a little bit about fault tolerance. It can help us out on tuning filters, really important on that. Measure crystal frequencies, attenuation, ferrite properties, can help match lengths of coax for arrays. Like when we have like 4 different antennas, all exactly the same, how do we connect that 4 different pieces of coax into one piece of coax that comes into our receiver? So all of those pieces of coax have to be cut exactly the same length, and they all have to be exactly in phase. So The VNA can tell us that things are exactly in phase. Helps us in the process of tuning repeater duplexers. So let's get started with our brand new Nano VNA that we just ordered from Amazon and got out of the box here. First thing we want to do is obviously charge the battery in it. So it takes a couple hours to get that battery fully charged. So once we got that charged, now we can turn it on and we can start mucking with it. The first thing we want to do is there's a screen that you can bring up that will tell you what version software it is. And you can check that against the website and see if that's the latest version. If not, you want to end up uploading the latest software. The next thing you want to do is calibrate it. This thing's a really sensitive um, device there, and you want to calibrate. Now, one of the things I'll mention about those three slugs there, um, there's better quality calibration slugs out there. I don't know if, for probably 80% of what we do, the ones they have in the kit are just fine. But if we're looking at trying to do a phased array or something like that, where we're really being picky on how things get combined, we might want to consider going to a more expensive calibration kit. Okay, so now that we got it calibrated, okay, so to learn how to use this device, I'm not going to bore you to death. I got some basic examples we'll walk through here, but if you have any questions, there is just a ton of YouTube stuff out there and other discussion forums and stuff that will do a far, far better of explaining how to use this device and how to end up getting the most out of it. It's really cool to go through those YouTubes and figure out how this device works. Also, grabbing that little demo kit board, um, play around with that. And so that's a good starting point to learn what the thing can do and what those different waveforms look like. So now that you've got some basic understanding of it and you're a danger on how to end up setting this thing up to yourself, let's take a look and let's take a look at an antenna and see what we can see there. And we'll also take a look at a bandpass filter and see what that tells us with this device. So before we get quite to, so remember this device is a touchscreen, so you don't have a keyboard or anything like that. Everything goes through that touchscreen. So trying to use your fingers to navigate through that, even on the 4-inch and especially the 2.8, it just doesn't work. And you just get used to either using that guitar pick or the stylus. It makes getting through those the menus a lot easier. Another thing is that I think they still ship with it, and I'm not sure about the currently, but if not, on the wiki and on the website, they have a quick start menu guide. So the menu is what you're looking for. Get that quick start guide, print it out, and make sure you just put it in the box that you end up carrying around that antenna analyzer in, because knowing where you want to get to as far as setting parameters, then you can walk back through the uh, menu that you have to step through in order to get that way. It's kind of a way of reverse engineering. So if I want to take and set a certain trace to be able to look at SWR, I can go back to find my SWR, and then I can work back through how to set my trace. I can work back through the opening menus in order to get to that point to set that up. So just remember to print out that quick start menu guide, and that'll save you a lot of hunt and peck and as far as getting through things. So, not to scare you, but for the current production of the Nano VNA, this is what the menu looks like. So personally, I have the older F version and the newer version is the H version. So on that H version, this is what the menu looks like. So believe me, it is absolutely amazing what this thing can do. It's not like a full scale or a, a lab type of or a Nano VNA, but I'll tell you what, it sure has a lot of stuff in it. So looking up in the upper left-hand corner, that's your opening display. That's the opening. So when you open that up, you're going to have that menu setting there. So it'll show the display, marker, stimulus, cal, recall, configuration, and pause. I'm not sure. Anyway, they got pause in there. Um, recall, excuse me. Recall is once you get finished setting things up, you get things calibrated, you get it configured for a certain band, you end up saving it into one of seven memories. So when you save it into the memory, let's say you have something all set up for 40 meters to really look at 40 meters. So that means you've calibrated for 40 meters, you have your SWR set up, you have um, your impedance set up. If you like a Smith chart, it's set up. Um, but you can get everything configured. And when you do a save of that, you can see down on the bottom left-hand corner there, you have your save and you have your recall. Save is saving it into the one of seven locations. One of the things you want to do is take a little note because whenever you set up some of these scenarios, you're going to be saving them and you like to know that, okay, I saved all my configuration in save number 3 for 40 meters. So you can, if you have a little note on what you have saved there, you can't go back and relabel those things, but at least you can go back and with your notes, you can recall what you got there. So the next one
Hey,
is
Mike,
stimulus. Yo,
I am able to relabel mine.
you are?
Yeah,
Okay, so
I've been able to relabel mine. I
I
just wanted to let
take
you know
that
that.
back. Okay, okay, the one that I tried wasn't letting me doing it. So um okay, so you can relabel it so you can put your own markers in there, what's going on. The next one I want to hit on is stimulus. Um there's a lot of jargon that comes out of I'm not sure where, but there are a few things in here you have to uh uh learn to deal with because um, they're a little bit different language and it takes a little bit of time to figure out how to do things. So stimulus means setting your frequency. If you go over to the right of that, it goes into start menu. I think I can go, yeah, here we go. So, so if you hit stimulus, so you have two ways of setting your frequencies. You can set your start frequency and your stop. So you're beginning your end frequency on what you either want to calibrate, what you want to look at, or what you're going to end up scanning. That's one way of doing it. Another way of doing it, like if you know that you're trying to look at just something very particular at a very particular frequency, you can enter that center frequency and then you can set the span. In other words, how wide you want to go. Like if you wanted to look at 40 meter FT8, that's 14.0 uh 7.5, I think it's 7.3, 7.5 or 7.4, something like that. And then you can set your bandwidth to 10 kilohertz, and then you can get all of that information in there looking at that. So that's the way you set your frequency. But you're always using this for your either calibration or for what you're looking at. You're always looking at always setting that frequency one way or the other. So let's move on to calibration on how that works. So calibration procedures. So this basically assures the accuracy. Yeah, the machine's pretty darn accurate, but this just kind of, let's say, sharpens the pencil in there and makes it really, really accurate there. So when you're calibrating it, there's basically four things that you're doing there. You have a short plug, you have an open plug, you have a load plug, which is a 50 ohm, and then you have a through plug. And that's where you take the other part. You have two connectors. You basically put a loop on those two connectors on that Nano VNA to check the through calibration. So it uses that information to correct any internal characteristics that aren't quite right and corrects that for your testing. The Nano VNA will walk you through the calibration step, but the key thing is once you get finished with that, you need to make sure that you save that calibration. And it's, I'll just say that you don't really want to do a calibration of like from 10 kilohertz to 1.5 gig. Um, that's not going to give you the kind of accuracy that you really want. What you really want to do is look at something like a whole ham band. Do that calibration for that particular ham band, like 40 meters, from 14 megahertz to 14.35. But you want to do that calibration over that band and save that. But that's kind of the first thing that you do is you want to make sure you save it. Okay, the next thing that you want to do is that once you walked all the way through that calibration process, you want to, okay, that just shows that in that menu there, down at the bottom there, there is a correction there. When you hit done, that's supposed to take you over to the save part, and that'll go through there and save or let you save that information wherever you need to. So let's look at this is what your calibration screen looks like. And here uh, I'm actually doing a calibration over 1 megahertz. If you look down to the lower left-hand bottom, shows you the start frequency of 1 megahertz. And over on the right bottom, it shows you that I'm going to 30 megahertz. So that's the entire HF band. So I'm saving that as my reference calibration. The just for information there in the upper left there, actually you can see on port one. On port one, that's the 50 ohm load that I have in there. On that 51 ohm load, you can see that's the yellow line. And if you look in the upper left, it shows your SWR as a 1.0. So that's a 1-to-1 match. The next one of interest is the number 2 there is the blue line, and that's shows R, and that's your standard resistance. There it's showing 50 ohms, and that's exactly what that thing's supposed to be. Um, so then the next one is the reactance, which is the blue, or excuse me, green one. And I believe that is supposed to be representing 9 milliohms, if I'm correct. I think it's a large M if it's megohms. And but obviously at this point it should be negligible as far as any type of reactance. So that's what you expect to see to validate that you have straight line all the way across that entire sweep, and everything looks okie dokie. So that's a good save, good calibration. Okay. Here we go. Let's see. What was this one? Oh, this one here just basically takes you through the steps there. When you're doing your calibration over on the right hand side, you can see it shows open, short, load. And as you go through each one of those steps there, it will kind of gray itself out, saying that you've already done that particular calibration. So it'll confirm what you have there. And then when you get all finished, you hit done and go off and save what you've done. Okay, so this one I've already talked about. So the other thing that I want to mention is over on the left-hand side of the screen there in the center is kind of calibration status. So it shows C3 there at the very top. That means that I stored that information in save area 3. That's the key thing. So if you want to figure out where that stuff was saved from or where you recalled it from, that little guy right there will tell you what's going on. There's other things that tells you as far as mm, uh, in that little column there as far as what got calibrated. If you see a C star, that means that that calibration is missing. You haven't saved or you don't have a calibration yet for that um, area. So let's go to a 20-meter beam or a 20-meter antenna. And so what I did was a sweep of this to kind of show what's going on. Those markers that we have there, those markers are labeled 1. That shows where the cursor is at. So that cursor is setting right at, and that's where I'm going to, where it derives all these numbers that we're going to be looking at there. So that cursor shows that I'm setting right at 14.075, which is the FT8 band for 20 meters. So it's showing that if you look on the upper left, it shows that I have an SWR 1.38. If you look down at the curved line there at the very bottom one, that's the SWR line. And if you kind of look across to the right side there, that ledger on the right side there represents the SWR. And so that should come out to 1.38. So I have a resistance there of setting at 42.1 ohms, and my reactance is 12.5 ohms, but not quite a perfect match for getting a one-to-one SWR. So this guy, the sweep here, if you notice that it starts at 13.9. So just as it comes into the 20-meter band is where I have the best SWR down there. So it drops down to maybe about 1.2 to 1. But that's not where it should be. That little bump right there should be further over to the right, more in the center of the whole band there. So anyway, that gives you a really good picture of exactly what your antenna looks like, and gives you the clues on what you need as far as moving things around on trying to make things a little bit better for you. So let's look at a one of the things I keep we keep talking about for field day and for 7QP is using bandpass filters. And we all kind of think that, well, these bandpass filters block everything up to the beginning of the frequency of a particular band and lets everything pass through that particular band. So this is a 20-meter bandpass filter. So it just passes everything through it. And then when it gets to the end of the band, it blocks everything. Well, let's look to see what the heck the thing really, really does. So here's a better blown up picture of that. So we have markers 1 and 2. That marker number 1 represents and you can see that that whole sweep that I'm looking at is from 12.5 megahertz all the way up to 16 megahertz. So those are way outside of that 20 meter band. So marker number one, that represents 14 megahertz. Marker number two, that represents 14.35 megahertz. So between marker one and marker two, that's the 20 meter band. So the top marker basically looks at how much energy I put into the bandpass and how much energy I get comes out of the bandpass. So you can see that way out there. I wish I'd put some other markers up there for um, basically when that bandpass became pretty active. You know, you can drop a couple, 2 or 3 dB and still have lots of activity that'll get through that bandpass filter. But you can see it's way out in front of that guy, of the 20 meter band. And you can see it goes way past the end of the 20 meter band. So that's kind of an illusion, kind of blown pieces that bandpass filter is, you know, that tight, and that's just not the way that they can design it. I'm sure you can throw more money at it and get better responses out of it. The next thing I'm very interested in is that, you know, whenever we insert any type of a filter into a system, there is always some level of loss, you know, except for maybe digital filters. But for any type of analog filter that we stick in there, we're going to have some level of loss. So over on the left-hand side, there's a little right arrow, and just below it says disk 99.9%. But that little yellow or orange arrow on the left side, that represents the reference signal that I'm putting out. So you can see between that line and where we have those first two markers on the yellow part, there's about a half a dB. So what it's telling us is that through that filter, we're losing a half a dB of signal. That's not much, but that is something as far as certain amount of losses that you're going to get from it. So the next one that I'll talk about is the kind of blue turquoise line, and that's the SWR. So that's how much energy gets reflected back as far as the transmit in the business end of that filter there. So you can see the SWR um, is still um, uh, it's not great. I don't have the numbers there, but as I remember, I think the SWR, the bottom one was like 1.25, the upper one was number one was like 1.5. So um, that kind of shows, you know, what you can expect from the SWR coming off of that filter. Just a filter. That's not including any other components that will add to that going through your system there. So I thought that was a really cool picture as far as giving me a really good visualization on how that bandpass filter is working and what it's doing for not working for me. Cool. So another really cool thing is that your Nano VNA, you can also connect that up to your computer, and you can run the whole shooting match from your PC. And actually, you get a lot more graphical information here, a lot more textual information that gets read out. And I really like running this thing through the the PC interface because of all the information. But if you're out in the field, that's not always an option. But if you're sitting at your desk at home, that is definitely an option. So I thought that was a pretty cool feature there to have that interface. Okay, so let's wrap things up. So any analyzer can be more than just an SWR meter. Okay, I shouldn't say any analyzer. An antenna analyzer, okay, can be more than any SWR meter. An antenna analyzer can help maximize your antenna system. So there's a lot of things you can learn from your antenna analyzer to help you tweak your antennas to make them work better for you. And then antenna analyzers can help you find problems in your antenna. So one of the things, and I have to say that this year I screwed up and didn't do it, but but about every year I'll go through using the PC interface and go through each one of my antennas and get profiles and print that information out and throw in a folder there. And then I just pull a folder out every year, compare it to what it's doing now. Every once in a while, I got a big surprise. I may not like the surprise, but it'll be different than what it was before. So I have to go back and figure out what the heck changed down there. Um, so before connecting coax to an antanalyzer, one of the things you want to do is that remember that this is a very, very sensitive test equipment. And if you have an antenna out there that especially wired, well, most any antenna out there, but it will collect a static charge. And you can very easily, and I've done this before. I blew up my little tiny soda antenna analyzer by connecting it up, and there was enough static charge on the antenna that ended up blowing the front end of that darn antenna analyzer out. So go through there and short out the center pin to the ground lead to make sure that you're not carrying any type of static electricity on there. So the Nano VNA is relatively inexpensive, and at those kinds of price points, that's a really inexpensive a piece of uh, really good test equipment that is worth doing an investment. Anyway, that provides an exceptional amount of graphical information about your antenna system. And before, all we had was numbers that told us what was going on. You know, but now we have more and more devices out there that really paints us a really good picture that really helps us to understand what's happening. Okay, to get the most benefit from the system, spend time watching the many, many YouTube videos on this subject. You'll learn a ton of things. I can't say that all of them are great, but there are a lot of those are really good that you may not understand everything the first pass, but watch it a couple times over again, and then you'll finally figure out what they're talking about and how everything kind of fits and it fits together. The Nano VNA has a PC interface like we talked about before, and that's a very, very valuable thing for keeping historical information and also seeing a big picture of what's going out there. So keep notes on what your setup is on your Nano VNA, like for your 5 to 7 different save locations, but keep notes on it on what area is being scanned and what it's set up for. It'll save you a lot of grief as far as hunting through things, those different locations, those different save locations to figure out what and how things were configured. So anyway, that's it, folks, and I am open for business um, for if you have any questions there.
I just a couple comments I'll add. One use I've got out of it that I really appreciate is being able to check where shorts are in coax. It'll tell you
Yeah.
about an inch if you got a short in your coax,
Isn't
and
that
then
amazing?
it is
I,
it's really amazing. And then the other thing I like with my antenna setup when using this Smith chart is it'll tell me which element I have to make longer or shorter. And so that makes it really easy to adjust my telescoping dipole.
wow, that's cool. Yeah, for you doing soda, that is really good as far as having something you can take in the field and you got a huge amount of information as far as knowing what the heck is going on. Another one that's also very good, and that's bad 259s. that either are broken loose or no longer soldered to the shield. That helps troubleshooting those things so you can wiggle things around and see on in real time on that display on what's going on.
I will
I'd just
confess,
like
I
to,
just ordered the VNA demo board. I didn't have that, and
Mhm.
for that price, yeah, I'm going to get that and learn some new things.
Yep, it's well worth it.
I'd just like to remind people that your Nano VNA does transmit a signal that sweeps across the band. And if you're
It
using
does.
it around other people in a contest, those people will hear the sweep come across the band on their receiver.
It does.
So, Anna, how do you know this?
I don't know, Mike. How do you know this?
I was just letting you take pounce on me a little bit more, but yeah. Not at 7QP, one of the things I had a new antenna. I had an antenna I'd used before, but I had never used it on a tower and a few other variables. And thought, too, I wonder how this thing works. Wonder if there's any problems with the coax or anything in putting it together. Um, and so during the 7QP, I pulled out my Nano VNA, connected it up, and did a sweep across 20 meters, and which lit up Anna as far as what's going on. And like, oh crap, man, what a dumb, stupid thing to do. But remember that that device is a transmitter, and actually, there's things that I've done, like I have a larger receiving array, and I've taken my Nano VNA, put a little stubby antenna on that, and set it in front of each array or each element on that array at a specific distance and specific height, and then came in and measured the signal that I was getting and made sure that that particular element was the right element that I was activating. And actually, that came up with found a wiring problem, or actually is a labeling problem on the product that I had. Any other comments about nano VNAs?
Mike, I came in late. Did you
Yep.
talk about? Yeah, it sounds like it was a great presentation. I mean, I guess I was halfway through it, so, and I'm familiar enough with the basics, to be okay skipping the beginning part. But did you talk about like measuring if you want to get a value for an inductor or capacitor, things like that? You can do that with a VNA.
Nope, I did not talk about that.
Yeah, no,
Uh, I
yeah, go ahead.
I gave a list of a lot of the things that you can do, and that was not an all-inclusive list,
Right.
but all kinds of basic stuff that you can do. But yeah, with a nano VNA, you can actually look at tune resident circuits and figure out what it's doing, and you can figure out how to make adjustments.
No, it's very cool. Yeah. So we talked about, well, I'll send you an email regarding what we talked about at Swap Meet, at Swaptoberfest on
Mhm.
Saturday. So very inspiring. Thank you.
Yep. So that's it, folks. Thanks for listening.
Thank you.
Thanks for
Anthony?
talking.
Yeah.
Yeah, thanks very much, Mike. That was more toys that, well, after, oh, I got mine actually sitting in the case right next to me. That was one of the first things I did when I got mine was I also went to Amazon and got one of the a nice little hard case, and so I've got, and the background thing's not working, but I actually have a nice, all the stuff in an actual case now that's a lot easier to organize and manage. And that way you have all the little cables and test
Yeah.
loads and slugs and everything ready to go. So
Yeah, because this is my bag of all my test stuff, all my connectors and stuff like that in a Ziploc. It'd be nice to have it in a nice case.
Hmm.
I bought a tiny little Harbor Freight case for mine, so it
Uh,
works okay.
yeah,
Gee,
it's not really a useful tool until you have acquired and put it in some sort of knockoff Pelican hard case kind of thing. So
yeah, right. So somebody should do maybe the next talk on the tiny SA, the spectrum analyzer, Mike.
Yeah. Um, I was thinking about that. I also recently picked up a tiny essay, and the newer one, the 4-inch screen, has a LNA in it, low noise amplifier, which will get that thing down to almost a minus 120 dB, which is really a small signal. You still have to do a bit of filtering on it, and there's lots of math that goes on there on inside there that does a pretty good job of flattening things out. But it's a certainly amazing equipment. I plan on using it more for trying to find electrical noise in and around the house and a few other places.
I've heard that the Nano SA is not as great an SA as the Nano VNA is a VNA. So, meaning that it while the Nano VNA is good enough for most ham stuff, the Nano SA is quite less impressive, is what I've heard from my sources. But I have not had one. I can't speak to it
Yeah.
authoritatively.
Okay. Now, do you know which generation that is in context there?
I don't know. I haven't heard in a while, but yeah, my people that like the folks that I
Well,
interact with that like test gear um, are say good things about the Nano VNA, but not as good things about the Nano SA.
Hmm.
yeah.
That doesn't mean it's a piece of junk because it's not. You just
No.
have to calibrate your expectations about what you see. Say folks that I'm talking to say it is not as good as like a Rigel 805 or a Siglent, right?
Yeah.
But
No.
those also cost $1,500.
And I would not use it for tweaking a set of cans.
Yeah,
I would not look at it for being definitive. I'm looking at IMD.
sure.
Uh, but there's enough information in there to tell you if you're in the ballpark.
Yep, exactly.
Well, is it the dynamic range you're talking about there, Anna? Because yeah, I would imagine it's limited, but it might be enough to do something like a IMD check or a suppression check, something like that for harmonics.
I mean, my understanding is it's in the ballpark. It's a useful tool, but if you're doing stuff that you care about, it's not a instrument that you use to do something that you really care about.
Mm,
As opposed to the Nano VNA, where what I hear is that it is good enough to do things that you care about, right?
sure.
Mhm.
Yeah.
I mean, a part of this is the price differential between a decent SA and a nano SA, and the price differential between a decent VNA and the nano VNA. A decent, more lab grade SA is, like the 805 or the Siglent equivalent is like $1,500. A decent lab grade VNA is like 15,000. So the difference in what you get for the price differential is a whole lot more on a nano VNA than a nano SA. But your mileage may vary. If it works for you, then good on you. And you're only out, $1,500 or so. So
Well, yeah, because if Mike, your LNA gets the noise floor down to 100 minus 120, 125 dB, that sounds pretty good. I think right now,
That's
just
I
staying
think a
with it.
part of it is also resolution bandwidth is not real great on the nano,
Oh, okay.
right?
Yeah.
So
that's
RBW
that's
is
where you did. Yep, that's where it hurts. That's the part that's a soft point. It just doesn't have that resolution bandwidth.
Oh, okay. So for IMD, looking at IMD spectra,
yeah,
they might not be able to do it with peaks that are close together.
right.
Yeah.
Mhm.
Again, not telling nobody not to buy one or get familiar with it or anything, and know what an SA is and how to use it, because it is an invaluable tool when you need one, especially if you're going to be building stuff and care about that. But yeah, just realize the instrument that you're using and its limitations.
Right. Well, I'm going to use it. We're going to be putting on a general license course here soon, and I will use it to demonstrate an oscillator, probably, and a sweep, changing the frequency of the oscillator, things like that, so they can actually watch the peak
Sure.
move, that kind, for educational things. I'm sure it's great.
Visualization rather than measurement, right? I mean,
Right.
that's a big piece of thing. There's a one thing to see a picture of what you're looking at and get an idea of what's going on. It's another thing to be trying to do measurements off of that.
Mhm.
And that's where you get into the higher end instruments.
Yeah, of course. Yeah.